Good afternoon, good morning, or good evening. Welcome to Webinar 6, organized by the National University of Singapore Environmental Research Institute, or NERI in short. I am Professor Hao Yong Ng, Director of NERI. It is my great pleasure to chair this webinar this afternoon. Today, the speaker for the talks on simulation of wastewater treatment using hybrid model is Dr. Ching Kwek Pooi. Let me first introduce him. Dr. Pooi is currently a research fellow at NUS Environmental Research Institute. He was my PhD student and he was conferred PhD in Environmental Engineering degree in June 2020. During his PhD program, he developed a model to predict the performance of petrochemical industrial wastewater treatment. The model predicts the biomass growth, nitritation and nitritation rate, organics removal, as well as the active biomass within the system. He used a combination of laboratory experiments and numeric simulations to validate the models and applied the models to make field-scale predictions. Currently, he's investigating the application of this hybrid model for the optimization of wastewater treatment plants. So without further ado, I'll pass the floor to Dr. Pooi for his presentation. Dr. Pooi, please.
Thank you, Prof. Ng.
All right, so sorry, before you begin, for all the attendees, if you have any questions, please feel free to type your question in the question and answer panel. And then if you like the question, please do click the thumbs up so that we know which question is of interest to the attendees. Thank you. All right, Dr. Pooi, please proceed.
Thank you, Prof. Ng. Good afternoon, everyone. My name is Ching Kwek, and thank you all for taking your time to attend my webinar. I'm from the National University of Singapore Environmental Research Institute. Today, I will be presenting about my work, which is the simulation of wastewater treatment using hybrid model. Wastewater treatment is a crucial process in the modern society. Both human and industries produces wastewater, and wastewater treatment plant will convert them into harmless effluent to be discharged safely into the environment or for reuse for various purposes. In wastewater treatment, biological treatment is often preferred due to its low cost. However, majority of the wastewater biological treatment plants around the world are not operating at their optimal condition, resulting in huge energy wastage and even non-compliance discharge. This is even more pronounced in industrial wastewater treatment, where different processes produces wastewater of varying characteristics. In addition, uncertainties in operating hours often result in varying volume as well. In wastewater treatment, aeration is one of the biggest energy consumption in the plant. In aerobic treatment, air is supplied to allow the bacteria to break down the contaminant. The aeration process, however, consumes up to 50% of the total plant consumption, with up to 30% of the plant total energy wasted due to poor control. This means that the plant actually supplied more air than is actually required. Non-compliance discharge is another issue faced by wastewater treatment plant. With increasing environmental awareness, discharge limit around the world is getting more stringent. Non-compliance discharge will result in massive fine and pose risk to the public health and environment. Since 2014, 119 companies has been charged for illegal discharge in Singapore. In fact, we can use modeling to address this issue. In wastewater treatment, modeling is often used to design, optimize, and upgrade existing wastewater treatment plant. It also allows the operator to understand the effects of various parameters on the treatment performance, allowing them to predict effluent quality and to monitor plant performance. There are two types of models widely used in the wastewater treatment system, namely the mechanistic model and the statistical, or often known as the machine learning model. Let me go through the mechanistic model first. Mechanistic models are based on fundamental concepts and equations. The physical and biochemical principle constitute the equation. But because of that, calibration is often required as most plants differ from the other. However, in most scenarios, average values are often used, which resulted in the inaccuracy in simulation result. There are examples of wastewater treatment mechanistic models are the anaerobic digestion model as well as the aerobic digestion model, aerobic sludge model. Machine learning model is another well-known model. Developed in the mid-1900s, machine learning model has improved significantly over years through data mining and collection. Most notably, the AlphaGo, which uses the Monte Carlo tree search algorithm. AlphaGo is known to be able to defeat the best human Go player. There are numerous studies on the application of machine learning model in wastewater treatment performance, achieving very high accuracy of 0.95. However, its application is highly dependent on the quantity and quality of data. And it is also a black box model, so one will not be able to know how the equation correlate with each other. This brings us to the hybrid model. Hybrid model is a combination of mechanistic and machine learning model. We can use machine learning model to compensate the shortcoming of mechanistic model, while the hybrid model is also more robust than pure machine learning due to its presence of fundamental principle in the model. So what do I mean by this? In these two examples, there's a parallel hybrid model and a zero hybrid model. In the parallel hybrid model, the mechanistic model will calculate the treatment performance, while the machine learning model will calibrate the difference between the measured and simulated data, compensating for the inaccuracy of the mechanistic model. In the zero hybrid model, the machine learning model will provide the unknown parameters to the mechanistic model. The mechanistic model then predicts the treatment performance. For example, in this scenario, the zero hybrid model, the machine learning model will predict parameters such as the U, the maximum substrate uptake rate of cyanide, which will then be fed into the mechanistic model for a more accurate output. In this presentation, we'll be showing our proprietary hybrid model, which is actually a combination of a parallel and serial hybrid model, which further improve the prediction. We have actually done some work using the hybrid model, and we will be showing the result later. As seen in the diagram, the influence data will be fed into both mechanistic and machine learning model. The mechanistic model will also receive information from the machine learning model, while the machine learning model will receive information from the mechanistic model. They will iterate within each other and then come out with the predicted effluent output. This is some preliminary result. So in this lab scale reactor treating domestic wastewater, we can see that the hybrid model actually outperformed the pure mechanistic model. The root mean square error was reduced to 6.6, while the mean average percentage error is reduced to 21%. Please do take note that the data is actually taken twice a week. So with more data, we can actually improve the simulation. The hybrid model was able to outperform the mechanistic model, as the mechanistic model requires careful calibration. For example, in mechanistic model, one will require to fractionate the COD into different components, which takes about a day or two to do it. But every batches of wastewater is different, and hence it is actually not practical, as the wastewater would have actually been treated and discharged before the experimental results are out. Hence, average value are often used as mentioned previously. The hybrid model, however, do not require such careful calibration, and it is also still be able to come out with good result. We have implemented the model in industrial wastewater treatment system as well. In this experiment, an MBR was set up to treat pharmaceutical wastewater. From the figure, similarly, we can see that the hybrid model outperformed the mechanistic model, reducing the root mean square error and the percentage error. It's actually also be able to capture the trend better, being able to predict the spike in the effluent COD in day 80. The correlation has also been increased to more than 0.8 as well. So prior to both of these simulation, the lab-scale industrial wastewater and domestic wastewater reactor were actually in operation for a year, and the data collected was actually used for the training of the machine learning model and calibration of the mechanistic model. So these data are actually simulation after the training. So this shows that the hybrid model is actually actually able to be implemented in both industrial and municipal wastewater treatment. While both results are both lab scale, we have also expanded our work into full-scale treatment plant. In this short 2 weeks work, we use our model to simulate the full-scale municipal treatment plant. We are able to achieve very good result with absolute error of less than 5 ppm and percentage error of less than 15%. The correlation was actually more than 0.95, which is actually higher than that of pure machine learning. Um, However, one actually may argue that domestic wastewater treatment in full scale is actually very stable and hence are much more stable than industrial wastewater, and hence the simulation, that's why is much better than the lab scale. So we actually use our work in industrial wastewater treatment plant as well. So in this full-scale industrial wastewater treatment plant, we apply our model, and from the diagram, we can see that our model is actually able to achieve good result with percentage error of 15% and correlation of more than 0.9. The results are actually from both the full-scale reactor, the results are actually better than the lab scale study, primarily due to the fact that the plant actually do daily sampling, which provided us with much more data sample, and we will be able to train and calibrate our model more better. The simulation will This shows that the simulation actually improves significantly with more data point and with better calibration as well. Showing the importance of daily sampling. The model can also simulate solids concentration. In this diagram, one can see that the model is able to simulate the mixed liquor concentration of domestic wastewater treatment with great accuracy. The simulation followed the trend well, and the percentage error is less than 10%. However, as we do not know the plant operation and how they collect the sample, this might explain why some of the data is actually deviate from that of the simulation. But nonetheless, we can actually see that the trend of both the measured and simulated is going towards the same direction. In addition, we do not have data on the plant biomass disposal. Um, According to the operator, they dispose their biomass through MLSS measurement. So once they measure the MLSS, then they will try to keep it within the range. So from this, we can actually use our model, as our model will be able to predict the biomass growth, and we'll be able to know if the biomass will be within the range prior to that of the measurement. We also use our model to predict solids concentration in industrial wastewater treatment. The result is actually not as good as the domestic counterpart, similarly due to the fact that we lack the biomass information and we do not have the discharge information, the solids retention time, etc. Nonetheless, it is also still a good indication to allow the engineer to know how much biomass growth there will be per day, and the engineer can actually make informed decision on how much biomass to be disposed daily. This might not be an issue for tropical countries like Singapore, but however, for countries with 4 seasons, it is actually very important that the biomass within the system is kept within range. This is because when temperature drops, the processes such as nitrification and the bio-P removal will be affected greatly. And hence, during the winter time, they actually will try to retain as much biomass as possible. And with this, with our simulation, with our model, we'll be able to give them more information on how the biomass is able to affect the process, how much biomass to be retained within the system such that their processes such as nitrification and bio-P removal will not be affected adversely. So the solid concentration will actually be important to ensure that the processes will be worked as not per norm and will be able to meet the discharge limit. So due to its accuracy, the hybrid model can also serve as a fault detection. So from the graph, you can actually see that the simulated value follows closely to the measured value all the way to day 103. On day 103, the measured value actually differed greatly from the simulated value. This actually means two things. Either the equipment is involved in nitrification process is damaged or the simulation is off. Our team began to then check the system and found out that the pH control is actually damaged. pH control, nitrification process requires careful pH control, and with the pH control damage, it will actually cause the nitrification process to be affected and hence the simulation to be off. So from day 103 onwards, manual pH control was done, and the pH control was actually replaced on day 135. And after that, the measured value actually is actually very closely correlated to the simulated value again. So this shows that this also proves that the model can actually be used as a fault detection as well. Actually, prior to this, upon closer inspection, one can actually observe that prior to the breakdown of the pH control, the measured value actually start to deviate from the simulated value as seen in the orange box. So from the orange box, we can see that the pH is the measured nitrate actually fluctuate around the simulated value. So this gives us a potential indication that we can suspect that the pH controller is actually breaking down since it's actually start to break down since day 50 of operation. Do take note that this is actually industrial wastewater treatment, and the industrial wastewater treatment, the incoming pH will change greatly, and which then actually affects the nitrification process. In the introduction, I actually mentioned that how models can be used for aeration control. Our hybrid model is actually able to calculate the oxygen demand. As seen in the slide, the oxygen demand actually changes with time. This information will actually be very useful for the operator, as the operator can then adjust the aerator to meet the necessary oxygen demand, reducing the instances of over-aerating and reduce energy wastage. With that, we estimated that the implementation of the hybrid model will result in an estimated saving of approximately 20% to municipal wastewater treatment, and it may be higher for industrial wastewater treatment. So how can one actually correlate the aerator to the oxygen requirement is through there are actually processes, fundamental calculation that correlates the aerator to the oxygen demand. So with that, we can actually calculate back calculate using the information of the required oxygen. We then can calculate the blower capacity to meet the oxygen demand. With that, we have come out with a patent pending hybrid model that is able to give us highly accurate simulation, which allow us to have predictive control and recommendation system. We can also calculate the biomass growth so that the operator will be able to maintain the biomass concentration. The hybrid model is also able to come out with fault detection, and predictive fault control can actually allow operator to maintain the equipment instead of repairing them. This reduces the OpEx cost. Lastly, the hybrid model is also potentially be able to use for energy wastage reduction through aeration control, through careful aeration control. So I thank you for the attendance, and once again, my name is Ching Kwek, and you can contact me through my email ckpooi@nus.edu.sg. Thank you.
All right, thank you, Dr. Pooi. Now I'd like to open the floor to all the attendees for any question that you may have. So please feel free to key in your questions. Okay, one of this first question is from Wei Hao. Do you compare the model with machine learning model?
Okay, so actually we did compare with the machine learning model. So what happened is for the lab scale, it's actually not meaningful because in the lab scale system, we only measure the data twice a week. And with a 1 year period of data, there's only 100 data. And this is actually not sufficient for machine learning. But we did use machine learning for the full scale plant. And actually, it's actually not that great because for mechanistic model, we actually calculate the time step wise. So with that, right, we can actually follow the trend better. But for pure machine learning, right, it will actually be more jagged. Yeah. So we did compare the model, and our model is actually superior than the pure machine learning model.
Okay. All right. Any other questions from the audience or the participant? Maybe like one question from Ching Kwek is that in all these simulation, what are the major challenge that you that you encountered that affect the accuracy of modeling?
So major challenges includes, for example, in the industrial wastewater, sometimes there's illegal discharge, and then we are unable to capture the data, and it will not be because currently what we are doing are grab sample, and we'll actually gradually move to sensors. So with grab sample, if we do not capture the data, it will actually affect the model result. The measured result will actually deviate greatly from the model result. Yeah.
So in another word is that in all this simulation is basically based on the organics that are biodegradable. So in the event that there's any accidental or discharge of stuff or organics or heavy metal, they're not supposed to be inside your wastewater, and they are inhibitory or to the bacteria, then your modeling will break down. I believe so. Yeah.
Correct. Yes. Unless unless we implement the inhibition factor in, but yeah, we can do that, but yeah, we did not.
Yeah, you can't do it easily because
Yeah.
let's say somebody dump heavy metal to
Yeah.
your treatment plant, so all the biosystem will fail, right?
Yeah.
So that can never be able to capture by the model. So certainly this model will work if there's no extreme abnormality, right? Like heavy metal discharge, or suddenly there's a huge VOC,
Yeah.
coming to a treatment plant, especially industrial wastewater treatment plant.
Mm.
Of course, the plant itself, if it is very big, okay, then this kind of event should be not common, because of the catchment capacity.
Yeah.
To achieve equalization and dilution effects. All right, thank you. So any other question from the audience? Okay, there's another one. How does your model compare to the commercial software? Are there any advantages and disadvantages?
Okay, commercial software. What should I say? There are numerous commercial software out in the market. So Currently, if you were to compare to pure mechanistic as shown in the slide, ours would be slightly better in terms of the prediction accuracy. Yeah. So there are also other commercial software like that uses ammonia set point, but because our system our model actually uses both ammonia and COD as set point. So this might be more useful in the industrial setting, where in some case where in industries they might not even have ammonia inside their wastewater. Yeah, so this is one advantage over the commercial software. Okay,
Okay.
do you try the simulation, the process
Okay,
of
next question. Did you try the simulation of the process in anaerobic MBR? What is the difference from aerobic process? Any difficulties in simulating anaerobic process?
Okay, we tried anaerobic process as well. Anaerobic process actually, yeah, it's actually much more difficult because in anaerobic process there are more inhibitory substance or even more stuff that can inhibit the treatment process. We're actually doing that now, and we are in the midst of developing the anaerobic model for the simulation of wastewater treatment, anaerobic wastewater treatment processes. Yeah, actually we can try the simulation of the anaerobic MBR, but yeah, but let's wait for our model to be fully developed first. Yeah.
Okay. All right, next question. Does your model prediction carry out based on regression analysis of future forecasts? If it is future prediction, what is the prediction duration?
Okay, thank you for the question. So for the future, it's actually for future forecasting. And the future forecasting is typically about 1 HRT because when the wastewater come in, we can more or less predict what is the wastewater 1 HRT later. Yeah, in most plant they use plug flow reactor, so the prediction actually is one HRT away. It is we can't predict the effluent if we do not know what's the influent coming in first. So yeah.
So if you recap it, certainly prediction is of course you can predict far ahead, right? So the question here is that whether it is meaningful, whether it's useful, right? So if you look at all these simulation software system, or the key here is that we need to predict accurately because this is the most fundamental of any simulation. And simulation, a real simulation system is that you have to use your past data for calibration, for machine learning, for kinetics, plus other methods to get all the kinetics parameter. So you have that model established that has been calibrated to a stream of specific kind of wastewater. And if you can predict very accurately, so the next question will be, what are you going to do with the information, right? So with that, with a good, accurate simulator, then you can start looking at how can you uh, capitalize on this model to save your energy, for example, of aeration, while at the same time making sure that the treated effluent meet the discharge regulation and whatever criteria you set for the effluent, right?
Mhm.
This is the, I would say, step number one that Dr. Pooi has done to predict as accurate as possible. And then there will be a series of questions that will come. Okay, how are you going to utilize this model for whatever target and objectives for the treatment plan? Yeah. Okay, any other question from the audience or attendees? Please feel free to ask any question you may have.
So actually to add on to what Prof. Ng has said, For example, the recycle ratio. So we can actually play around with the recycle ratio. Actually, not we, but we can actually write codes to allow people to play around with the recycle ratio. And then we'll to find out what is the optimal recycle ratio and still meet the discharge limit. This is actually more important in processes such as denitrification, where the aerobic tank is actually recycled back into the anaerobic.
Okay, next question. We have one question. Is the model developed specific to one type of industrial wastewater? Are we able to apply it to other types of wastewater?
Of course, we are able to apply it to all other type of wastewater that is actually biological treated, because the fundamental thing about this model is actually biological treatment. So but the thing is, for each model is actually developed for each specific plant. So for example, the model developed for plant A cannot be implemented for the model cannot be implemented for plant B unless they are actually treating wastewater that are of very similar characteristic, and they are actually of similar design. But in reality, plant A and plant B normally they have different hydraulic retention time, they have different design, etc. So the model is actually, for each type of plant we have to cater for them individually. Yeah.
Any other questions?
Oh yeah, so if you all do want to reach out to me, you all can always email me, yeah, for collaboration, or email Prof Ng
Yeah.
regarding, yeah.
Okay, another question. Will it be a time-consuming process to model each plant?
Currently, okay, so what we are actually doing is a time-consuming process. Uh, because we haven't streamlined how to do each plant, currently it's about 2 to 3 months to model each plant. But if we were to streamline the process, like make it modular, which we are actually doing it now, to make the process modular, you'll be actually we can actually implement the system into each plant in a very relatively short time. But this will actually have to depend on the data of the plant. Let's say if the plant do not have any pyro data, we can still implement the system but the benefits will not be seen immediately. Uh, it will be more of the system will be collecting data and then slowly improving the model, and gradually the full benefit of the model will kick in maybe after a few months, where we have sufficient data to calibrate the model and to train the to calibrate the mechanistic model and to train the machine learning model. But that being said, the mechanistic model can still be implemented in the plant, and we can immediately see the aeration benefits, because we can do the what's it called? There are numerous control for aeration, and which can be implemented into the plant immediately. Yeah.
All right, are there any more other questions? All right, one more. Could you predict membrane fouling using your model in MBR?
Okay. Theoretically, theoretically I can, but I have not tried it yet. So what happened is in an MBR system, fouling can be attributed to numerous type of foulants such as SMP, EPS, all this. So while the model can actually model the SMP, EPS production, uh, we will really need to know how each component contribute to the membrane fouling. Yeah, and then in addition to membrane fouling, in membrane fouling there's actually two phases. So the gradual increase and then the rapid increase. Uh, we we need to think about how to do that also. But yeah, in theoretically it can be done. Yeah, using the hybrid model through the machine learning portion and the EPS, SMP EPS portion to predict the membrane fouling. Yeah, I hope that answers your question.
So the answer is that you want to predict, certainly you can based on machine learning with data, and that's the one way to do it. Of course, if you want to go into fundamental simulation, it will be pretty challenging. Okay, of course, that model can be developed, in my opinion, if there's sufficient data to kind of relate the relationship. Of course, this is the more mechanistic model. So certainly, if you based on pure machine learning, I believe it can be done. Right, but the question is, of course, always an issue how accurate. And you want to combine with mechanistic model, I think that there's still quite a bit of work to be done in order to have that correlation. Because for people who work in membrane, you realize that there's a lot of study understanding membrane fouling, but to truly able to predict fouling is I haven't come across. Okay. Okay, any other questions? Any last question? Okay, if there's no more question, we will end this webinar shortly. So once again, thank you very much to all of you who has attended this webinar. And do feel free to contact us if you have any questions. You can always go to NERI website, and then you can ask any question, whether it is technical question or potential for collaboration, visits, whatever. We'll be more than happy to discuss with you. And now is webinar 6, so we do have a few webinar, another webinar tomorrow at 4 p.m. same time. It will be given by Associate Professor Leffer Olivia, talking about how to treat industrial wastewater. So once again, thank you all of you for attending the webinar, and we look forward to your participation tomorrow. All right, thank you. Have a nice day.
Thank you,
Bye-bye.
everyone.